Elif Erdine is an architect and researcher. Currently, she teaches at the Architectural Association AA School of Architecture, Emergent Technologies and Design Graduate Program. She is the program director of AA DLAB Visiting School and AA Istanbul Visiting School. She worked for Zaha Hadid Architects during 2006-2010. She received her BArch degree from Istanbul Technical University in 2003, high honors, and MArch degree from the AA Design Research Lab in 2006. Her research interests are the integration of algorithm generative design with large-scale digital fabrication tools and in physical computing. Ms. Elif Erdine, the floor is now yours.
Hi, good morning, everyone. Very happy to be here. Thank you again for inviting me for ASCAD, and I am going to share my screen. Yes. Can you see my screen? Yeah.
Yes, we can.
Great.
Yes, we can.
Perfect. So thanks again for the invitation. I'm very happy to be here with you all. And so I will be talking about the postgraduate program at the AA, Emergent Technologies and Design, and within the theme of ASCAD, how we make use of kind of hybrid workflows and hybrid technologies across scales and across different mediums, basically. And so what we mean by emergent technologies, it's really about addressing emerging problems that are existing in the world and how we address those problems and how we try to come up with solutions that integrate both traditional technologies as well as innovation and new technologies and techniques in the world. And so I thought that today I would talk about the kind of multifaceted nature of the architectural profession in general. And in my opinion, as architects, we're trying to resolve issues that, ultimately end in the production of space. Obviously, because architecture is a multifaceted field, and the answer to these questions of space production can be of completely different types and various natures. So, for example, obviously, the first solution that comes to mind is architectural solutions. These answers can also be at the ecological scale, which we deal with a lot in MTech. Urban solutions, material systems. They can be design processes, design methodologies, computational workflows. And they can even be software or applications. And so in MTech, all has been and all is about experimentation, all is process. For the past 20 years or so, we've been experimenting with novel computational methodologies, building systems, and all of our computational experiments and systems are calibrated from physical experimentation. So this is really what I want to talk about today, like how all of our physical experiments lead us to devise computational, let's say, workflows, and that's what creates the hybrid nature of our workflows in MTech. So it's really about understanding material behavior on a component and regional scale, quantifying them to later on develop more complex design processes and computational workflows. And so we believe that it is impossible to build on your knowledge from one project. And so we try not to use more than one technique in one project, and we approach research as a craft. Introducing material constraints and really working within the craftsman tradition and the atelier tradition. And obviously, all of these generally can be divided, let's say, into three big categories: digital, physical, and hybrid. And I must say that, you know, these may seem separate, but in the framework of architecture and how we approach design, actually they're very much integrated together, and we approach them as a kind of unified, let's say, discourse. But for the sake of the presentation, I just wanted to kind of divide them into these three different realms. So I'll start with the digital, and at the end of the day, I just want to emphasize that, you know, there's a lot of importance, obviously, in the digital and the physical, and how they come together to kind of formulate the hybrids. And so I guess you've heard this phrase before: form follows nature, right? So, but what we are really talking about here is not imitating the forms of nature, because this has already been done before. We are really interested in form following nature's processes, and what we can learn from these processes in nature, and how we can extract them and apply them for architectural and technological solutions. And what we are really talking about here is the evolutionary process in nature, the evolutionary principles. So, as I said, evolutionary principles, processes learned from nature, and how we can apply these processes to computation. So if we consider, let's say, three different fields as, let's say, evolutionary principles or biological principles, computation and design, which are actually quite integrated, we can create a bridge between evolutionary principles and design through computational design. So that's how we kind of utilize computational design in our workflows, in our computational and design workflows. And this bridge will ultimately create a feedback where, you know, design and computation influence one another through what we learn from nature, what we learn from biological principles. So biomimicry is one of the kind of principles that kind of guide us and that kind of lead us in our design research processes, which means basically the analysis of natural systems and extraction of principles for technological applications. And by looking at nature, we develop algorithms, let's say in this case, from the social behavior of insects, how local interactions lead to more complex behavior, and how we can apply these models as growth models in architecture. So, you know, there are very good kind of mathematical and computational models of these that are well documented in architecture and computer science, such as stigmergy, such as cellular automata. So, as I said, we study morphological precedents from nature. We understand their structures, their performance, their behavior, and then we really investigate how to apply the principles that we learn from nature into the architectural and technological problems that we're facing. And as I mentioned earlier, we're not interested in, let's say, bio-inspiration, but biomimicry. So really applying principles from nature for architectural solutions. We also use new technologies that are being developed, such as AR, VR, XR, in the realms of Unity and AR for participatory design purposes. We're very much interested in inclusive design strategies and how to use, let's say, gaming engines to facilitate participatory design processes. In this case, you're looking at a design problem, which was contextualized in the Hoxton area of London. How to, in this case, it was about how to kind of revive the public spaces in London through participatory design. And we are also interested in using these new technologies, and again, this is taking place in the realm of Unity for narrative purposes. So how our students can come up with narrative processes to explain their projects, basically. Not just, about the final product, but really talking about the entire process of design, how they came up with the concept and then started developing their ideas and started testing material behavior. At the same time, describing the kind of overall scale, so on and so forth. So what I'm trying to really kind of describe in today's presentation is the multifaceted nature of architecture, right? So architectural problems contain multiple scales, and the majority of the problems that we deal with in architecture have multiple different objectives. And that's why evolutionary computation, and in general, learning from nature is quite relevant, because obviously nature teaches us about the kind of complex nature of systems that emerge from the local interaction of different parts. So that really brings us to kind of question the role of the architect. This kind of way of enabling computation really necessitates us to think about the role of the architect. And I believe that when architects use these kinds of, let's say, computational tools and complex ways of problem solving, our role will change from coming up with a single solution to coming up with a question or a series of questions. So rather than designing a single solution, it's really about designing the problem. And that is really what we learn from nature and complex systems in nature. And that brings me to the question, or to the, let's say, principles of genetics and evolutionary computation. So it's really about, understanding graphing functions, multiple conflicting criteria. And through this process of running genetic algorithms, we can run obviously many generations and keep track of every single individual that is being created. And it really necessitates us to think about the design problem, as I said, rather than thinking about a single solution, and really about understanding and evaluating the results and apply them for our design solutions later. And these techniques are in a way scalable. So we can come up with multiple design problems that are emerging in different parts of the world across different scales. So they can be either the material scale, as I said, urban scale, ecological scale, and really apply the kind of complex patterns and issues that are emerging in these different biomes and apply them for complex design problems. And moving on, how do we adopt these technologies when it comes to the actual building scale? How do we employ these skills? So I will talk a little bit about the kind of physical, let's say, nature of things, and again, how the physical problems allow us to create, again, hybrid solutions across different scales. And so in MTech, we've been working very much with timber for the past 2 decades or so, and we've been very much interested in advanced fabrication techniques with timber and physical computing. And I must say that in general, there is this culture of making at the AA and the joy of making, and basically learning by experimentation, learning by doing. And each of these projects have obviously different functions and different kind of fabrication and making processes. And as I touched on in the beginning of the presentation, we like to kind of focus on one technique in each project. and learn from that. And some of these structures that you see have been created in collaboration with different institutes, such as this one that was created in collaboration with ETH. And so, you know, we really we can call these as performance. And why do we call them performative? Because obviously, at the very least, they're self-standing structures. They need to react to various types of forces and loading conditions, right? Such as self-weight or wind behavior. This is another example from our collaboration with Arab. And they really all start with, let's say, some tabletop explorations by our students. And then, you know, kind of iterative nature of experimentation, large scale. We also have a very kind of interdisciplinary project on a structural scale. And just to kind of delve into kind of hybrid nature of our, let's say, interdisciplinary processes and our design workflows, I will talk about our recent collaboration with Hessel Studio that took place last year. And our structural consultants were Bureau Happold Engineering, and our life cycle assessment sponsor was One Click LCA. And this pavilion called the Re-Emerge was located on Bedford Square in front of the AA, and it was open to visitors for a month. So this is Bedford Square where the AA is located. And I will not delve too much into the physical, let's say, process or the physical experimentation, but I really want to kind of emphasize how those physical processes of experimentation informed our computational processes, what we learned from the physical experiments. So basically, based on the principles of sustainability, Hessel Studio asked us to keep the carbon footprint of this project to an absolute minimum. And therefore, we were asked to use only reclaimed wood. And of course, using reclaimed wood means that the system needs to be modular. And we also started to examine the life cycle assessment methods to measure the carbon footprint. And actually, we had not worked with, you know, life cycle assessment processes before, so it was quite interesting for us. So the fact that the system needed to be modular has obviously a couple of advantages. The efficiency of the system increases because we're working with similar, or let's say, the same design elements, in this case, timber beams. So it allows for streamlined fabrication, streamlined assembly and disassembly processes, and facilitating the addition or subtraction of these timber elements from the system. And as I said, the main idea was minimizing carbon footprint and analyzing the ecological impact. And through our research, what we found out was that construction waste, and in this case, timber planks, can be a very useful resource. And they kind of led this research to redesign timber for a lightweight outdoor structure and to highlight the ecological impact of the project from the early stages of the design. So we're looking at some of the earliest, let's say, timber planks that we found. We got in contact with recycling facilities in and around London. So these are the kind of like, this is the kind of average length, width, and timber that we could find. And because we were interested in creating a lightweight structure using these timber beams, rather than, let's say, stacking them vertically or horizontally, we started thinking about kerf banding and steam banding of timber elements. And again, relating to the ecological impact, we wanted to reduce the secondary materials. So we were looking into cross-slab joints and how to kind of, as I said, decrease secondary joiner elements. So at the end, we came up with this kind of system of design where we could kerf band and steam band these timber beams into these kind of curved timber, let's say, elements, which would then constitute these what we call the ribs that were attached to each other. And through the rotation of these ribs, we could come up with a structural system, basically a load-bearing system. And this is also became our let's say design proposal for Tallinn Architecture Biennale, and we were finalists in that competition as well at the same time. So these are just some process images. As I said, I will not talk too much about the physical process, but you're seeing some kind of early prototypes of our kerfing and steam banding. And, you know, our students created a lot of experiments using these principles of kerf banding and steam banding and how much curvature we could induce in these timber elements, basically, and where they fail and how they fail, and you know, what are the kind of extremes that we need to take into account. And at the same time, as I said earlier, we started looking into the life cycle assessment processes of using timber. So, and how we could use life cycle assessment, LCA, as a design driver in our computational workflows. And that really allowed us to consider not only the material itself, as in timber, but also the carbon emissions associated with its origins and transportation to Bedford Square. So it really emphasized a kind of comprehensive information for the preliminary design phase. And analysis of most types of plywood used for exterior construction versus solid wood planks actually shows that plywood's carbon emissions are significantly higher in preparation than solid wood planks. And at the same time, the same effect occurs when newly produced solid wood and reclaimed wood are compared. So we established, let's say, the principle that through the use of these reclaimed wood panels, we could reduce the carbon footprint. And at the same time, simultaneously, we were obviously analyzing the structure for its structural, let's say, performance. And in this process, you know, through our understanding of the material behavior, the life cycle assessment process, and structural performance, we integrated everything that we learned, as I said, material information, structural performance, carbon footprint, into a kind of streamlined computational workflow using the Wallace platform. So Wallace is an evolutionary engine for Grasshopper that has been developed by PhD researchers in MTech. And in this kind of collaboration, let's say, between architecture and computation through this evolutionary algorithm method, obviously there are, let's say, three important steps. One is the design problem, that's the first step. Then there is the evolutionary algorithm, and then there is the kind of selected solutions and how we analyze and evaluate those selected solutions to come up with let's say, a candidate to move forward, right? And so bookends are really the first and the last steps. And these are the important parts or the important processes for the architect to kind of think about and to come up with. We know what the computer is capable of, obviously, and that's taking kind of care of the evolutionary process. But as architects, we need to ask the right questions to come up with the, let's say, as I said, the design problem itself. That's the first step. And also to be able to analyze and evaluate the design solution space in the last step. So all of the kind of material, let's say, experiments that our students came up with were translated, let's say, into a series of lines of codes for the computer to kind of understand what is happening. Again, going back to the computer acting as a bridge between, let's say, design and natural processes, understanding nature's processes, in this case, understanding and translating material behavior. And the second step was to create a morphology. Sorry, 1 second. To create a morphology from, all these ribs and to kind of search the solution space by kind of looking into 3 fitness objectives. One was minimizing the height to width ratio. The second objective was minimizing the carbon footprint, as I said, through LCA. And the third objective was minimizing the displacement values through finite element analysis. So in this case, you're looking at, a solution space of, let's say, several hundred candidates. And obviously everything is numerical. So everything, we kind of understand performance through looking at these kind of graph functions and understanding really what they mean and how those different morphologies that you saw perform. And that kind of led us to come up with a design solution that we could construct within a certain time frame. And obviously documentation is also very important in this case, and how that kind of feeds back, all the kind of information about documentation feeds back into our computational processes. And what was also very kind of important for us in this case was that our students came up with a special application, a special app for visitors of the pavilion. It's an AR app, and it allows users to learn about the, let's say, the history of the pavilion, where these timber planks came from, kind of their story, the life cycle assessment of the pavilion, its design and manufacturing processes, as well as various kind of visualization options. And I just want to take you to an important step in this process, where we actually projected the pavilion itself in real time in a 1-to-1 scale. And that really helped us with the construction process, basically. So how to start the construction or the assembly process, that was quite helpful through using this AR app. So these are some say time-lapse videos of the construction process itself. It took around 5 days. Just jump to the final parts of it. Some final images taken by Studio Naro. And I just want to highlight this actually, this kind of final stage where we captured the pavilion itself through Matterport technology in order to create a point cloud. And the reason why we think this is quite important is that we could then overlay the final, let's say, physical pavilion with the computational design, and we could compare the deflections, as you can see. And why this is important is it's really because we can really learn from this process, you know, by using these kind of computational techniques. We can learn, you know, where the pavilion failed, how it failed. As you can see, there's some kind of deflection in the overhang area, and how this could be improved. And, you know, this is what we think the strength of computational processes lies, right? So we can then understand from what worked and what failed, and we can reflect on that, and we can improve on that in later iterations of our design workflows. And we won the Architizer A+ awards in the architecture and collaboration category with Hassel Studio, which is obviously a kind of a good outcome of this collaboration, because we really believe that there needs to be more collaboration between academia and practice to kind of improve our computational workflows and really to learn from each other. And that really takes me to the final part of my presentation. As I said, I started with the digital, moved on to the physical, and moving on to the hybrid. And obviously, as I said, actually in the framework of architecture, these are very much integrated with each other. And I really want to kind of emphasize the importance of both aspects, digital and physical, in this kind of hybrid realm in solving architectural problems. So going back to the initial part of my presentation, emergent technologies is really about, we're very much interested in solving emerging problems that are existing in the world. And these problems take place across scales. So it's really about emphasizing a multi-scalar design process and coming up with novel architectural solutions to existing design problems. And so I'm going to show very briefly kind of snippets, examples from our students' dissertations, thesis processes. So these solutions might be related, in this case, to food production capacity in cities through hydroponics, kinetic secondary facade systems that are designed, and where architectural properties are added and integrated with the architectural solution in order to reduce energy consumption by adapting into changing external conditions. In this case, we're looking into plastic recycling in Almeria, Spain. It's really about creating a rapid, lightweight assembly that is climatically responsive and hydro and thermally integrated farming system to sustain food production in arid conditions, and how that system can also enable a productive settlement for workers. In this case, you're looking into the context of India, mycelium growth, more specifically, relationships between material resonance, earthquake-resistant structures, and fabrication processes. So how to enable mycelium in order to create an earthquake-resistant architectural system, which then is configured into, in a larger scale, into kind of an urban settlement system. Robotic nomadism, a material system which can provide dwellings for nomadic pastoralists in sub-Saharan Africa using existing construction techniques and additive manufacturing. So again, studying vernacular precedents such as actively bent armature tents and earthen construction techniques, and applying these and integrating these, let's say, well-documented systems for novel robotic processes. In this case, adaptive floating settlements, integrating different strategies and design processes to address wave energy reduction and develop organizational logics of floating settlements. So again, understanding the context in every case. So in this case, the research was contextualized in a settlement in China. In this case, this research was conducted in strategizing, let's say, the use of ecological sand stabilization techniques to form wind deflection strategies. And this one that you're looking at was focused on a coastal region in Indonesia, where the research ambition was to generate ecologically resilient multifunction offshore structures for urban living through the study of coral grafting as a sheltered habitat for reef fish. And finally, the looking into the urban development of a high density settlement, in this case, Tokyo Bay, facing pluvial and fluvial flooding, is addressed, and the resilient design approach is investigated through the generation, analysis, and evaluation of an integrated hydrological system from base scale to the local scale, and really studying water dissipation strategies through offshore breakwaters, channeling strategies in order to develop a modified water network that can then be integrated with the urban, let's say, settlement system. These emerging problems can also be of social, let's say, scale. In this case, the problem of urban spaces and communication of people in urban space. And in this specific example, the thesis had a critical look at the way of using an urban space in London and trying to produce a material system and a mobile application AR app that people can use to create a positive and constructive interaction between themselves in urban space. So exploitation of cyber physical systems in public spaces as a means of increasing social mixing and social interaction. And it was very much focused on the notion of an anticipatory cycle and a data-driven structure, looking at inclusive strategies, quantifying them in an algorithmic manner to facilitate their implementation. And the architectural application was about an actuated origami structure that are explored in conjunction with a pneumatic mechanism for their actuation. And the final example that I would like to talk about addresses the lack of housing, basically, and this thesis aimed at presenting an automated system to create a collaborative design and construction network to solve, as I said, the problem of lack of housing in Singapore. Obviously, there's an increased demand for buildings that change over time, let's say, to adapt to newly emerging needs for different qualities and quantities of architectural information. And so this research really aimed at demonstrating a design workflow that can respond to dynamically changing environments over time with a bottom-up approach of design. A residential neighborhood in Singapore that can be reconfigured based on personal requirements of the users, and that can possess sustainable construction and material systems through timber that allow it to adapt to changes over time by altering the spatial configurations based on future requirements. And the methods that were investigated were advanced procedural design and artificial intelligence techniques. So we're looking at the kind of evolution of these spaces throughout years, in relation to the changing needs of the population in that specific context. And so the way I kind of would like to finalize is that, all of this obviously research, it's very important for us that you're looking at an image from our bookshelves in MTech. All of this research is documented into these books. that are then, shared with academia and practice through different media, through different publications across books, as well as journal publications, conference publications as well. And we're a team of architects, as well as engineers, as well as theoreticians, AR, XR developers, so it's very much interdisciplinary. And we very much value that interdisciplinary kind of nature of the program, as well as the students. Our students also come from different backgrounds. They're not just coming from architecture, but let's say structural engineering, different kind of streams of engineering, product design, so on and so forth. And so I guess you're familiar with this phrase, each generation must build its own city. This was posited by the futurists around 100 years ago. So what we try to do through these kind of hybrid processes of, making and computation and their kind of communication within each other is that how are we going to build our cities of the future? And I will leave it with that question. And thank you very much.